This is a quick how-to on applied optimization along with an example, which is my favorite. So applied optimization is saying, how do you make something fastest, cheapest, or make the most money, something like that. And it's a calculus approach. First off, you're going to be trying to understand the scenario and finding the variables, choosing the variables, and finding something called the objective function. That's the thing you're trying to optimize. Often you're going to be drawing a diagram, although not always. The objective function is the thing you're trying to find the minimum. You're going to be taking the derivative of that. And you're going to be finding the critical points. That's where the derivative is 0 or undefined. Sometimes there'll be endpoints that are involved. If the actual variables you have boundaries, that's just how it works. You have to deal with those. Then if you don't have endpoints, you can just worry about the first derivative test or the second derivative test. If you do have an endpoint, you ought to think about the extreme value theorem to find the optimum. So remember, extreme value theorem includes specific endpoints. These two are not so dependent on endpoints. Okay, on to maybe my favorite optimization problem. It turns out dogs can actually do this, apparently. They can estimate this optimum. But let's read this together. Standing at the edge of the beach with your dog, you throw a frisbee as far down the beach as you can. So, diagram is in order. You throw the frisbee, but it lands 100 feet out in the water. Oh no! There's 100 feet, okay? Your dog can run 22 feet per second, but it can only swim 5 feet per second. So you're down here somewhere. Let's pretend, I don't know where, here's my first variable. Let's pretend I'm standing Y down the beach. How far before standing directly across from the frisbee should your dog plunge into the water in order to get the frisbee as soon as possible? So the dog's gonna plunge into the frisbee here. How far, let's use the proverbial X for that. How far before the dog goes from running along the beach to running into the water? Well, this distance here is Y minus X. Y isn't changing, I just don't happen to know it. So maybe it's 200, maybe it's 500. That's not going to change, but X can. I've got that distance there going at 22 feet per second. I've got this distance. What is that distance? I guess it's the square root of 100 squared plus x squared using the Pythagorean theorem. So remember, what I'm supposed to do is I'm supposed to figure out an objective function. I'm trying to do an as soon as possible problem. So my objective function is not surprisingly going to be time. Okay? How much time? Well, let's imagine this is a certain number of feet and I can run it in 22 feet per second. So I'm going to take that number of feet and divide by 22 feet per second. That tells me how many seconds, right? So just practically, your objective function is going to calculate out how much of what you care about is happening. That's how many seconds I spend on the beach, or my dog spends on the beach. And this is how many feet the dog has to swim. Better the dog than me. And it can swim at 7 feet per second. Okay, so now it's time for me to take the derivative. This is the thing I'm trying to optimize, right? I want to know the slope here. And at the optimum, the slope is probably going to be 0. So t prime of x, let's see. The derivative of the numerator is -1. This is a constant, so you could say 1/22 times -1, -1/22. Here, let's see, that's all under the square root. You could put a 1/7 out in front or a 7 at the bottom. That's a constant. The derivative of this, using the chain rule, it's something to the 1/2. So it's 1/2 inside piece to the -1/2, or you could just put it in the denominator to start with. 100 squared plus x squared, right? So 1/2 goes in front, this to the -1/2, but then using the chain rule times the derivative of the inside, which is 2x. And I want to know where that's equal to 0. Notice it can't be undefined. This thing will never be 0. The 1/2 and the 2 cancel. So I've got something that looks like this. Let me put that over on the other side, just for convenience. So I've got x over 7 times that square root equals 1/22. I'm going to move the 22 over here, and move the square root over to the other side. So let's see, I have 22/7 x equals the square root of 100 squared plus x squared. I'm trying to solve for x, and it's kind of a mess here, right? I'd really like to know what it is. This is still finding that critical point. Let's see, so I'm going to square both sides. I've isolated the radical, by the way. This is the technique when you have a radical equation. Now I'm going to square both sides. Okay, so this is 22/7 squared. That's a big messy number. And the right side is a not so messy number, 100 squared. You could write 10,000 if you wanted. Okay, and now I'm going to get all my x's on one side. 22/7 squared. You could write that out if you want, but it's probably a mess. Minus 1. That's how many x squareds I have. Let's see. So x squared equals 100 squared over, let's see, 22/7 squared minus 1, right? Now, you realize that x shouldn't be a negative time. It shouldn't be a negative distance. So let's just assume we know it's the positive one. Okay, so I have x equals 100 over the square root of 22/7 squared, taking the square root of the right and the left, minus 1. Okay, and I could use a handy-dandy calculator to sort of try and figure out what that was. Let's see, so 100 divided by the square root of 22 divided by 7 squared minus 1. Let's see what happens there. Okay, about 33.6. 33.6 feet before there. So notice it's not quite square. You want to run more and swim less. That's not so surprising. Now, you might just say common sense tells you that that's a minimum, but if I was really going to be hardcore for the first derivative test, you'd say, okay, f prime, I know the first derivative is 0 at 33.6. What happens less and greater? Well, you could always plug in 0 here. If you plug in 0, and that's basically the dog running there and there, you can see that the derivative is negative 122. So the derivative is negative here, 0 here. You could plug in a point that's a little higher. You could plug in 40, for instance, here and there, and you'd actually get something that's positive. That tells you that this is a minimum. It minimizes time, right? This distance will get you the minimum time. Now, that's something that you can use with optimization, but it also makes practical sense. So I just want to close with, I've taken the liberty of typing that into Desmos and showing you what the picture looks like. Here's the equation, right? I just put in a 200 for y. You could put in a 500 and it wouldn't change it except for the height. And here's what my graph looks like, and you might say to yourself, yeah, it might vaguely be there. Luckily, Desmos is so cool, it'll actually highlight a dot for the minimum, and there we are. We got the right answer. It actually makes sense.